This is the Society for Light Treatment and Biological Rhythms ongoing webinar series. Today, we are very fortunate to have Dr. Stephen Lockley presenting. We have had a number of previous webinars, and they are available to view on our website at your convenience. Please do check out our website. Check out the upcoming meeting that is going to happen in June, the 24th to the 26th. It'll be virtual this year. The current program is posted from last year, and the vast majority of speakers have recommitted, and a new scientific program will be uploaded shortly. We do have an additional webinar coming up in April on the 14th from Diego Fernandez from the National Institute of Mental Health. Today's speaker is Dr. Stephen Lockley, Associate Professor of Medicine at Harvard Medical School, Neuroscientist at Brigham and Women's, Professor and VC Fellow at Surrey Sleep Research Center, the University of Surrey, where both he and I graduated from. So go Stags. Steve and I have had the great pleasure to work over the last couple of decades on a number of NIH and currently running studies for NASA on the International Space Station. It is my great honor and privilege to welcome Steve to today's webinar. Steve.
Thank you, John. If I can just share the screen. Okay, share, hopefully. Okay, how does that look?
Looks great.
Good, so thank you. Thanks very much, John, and to the organizing committee for inviting me to speak today. I have had the pleasure of working with John through our colleague and friend, Bud Brainard, now for decades. It is true, sadly, but it's been a fantastic relationship, and obviously I wouldn't really have been doing much of this work if it wasn't for Bud, and so certainly he's been a key person in this topic for me. So today we're going to talk about the non-visual effects of light, and I thought when I put the title in, its application in architecture. I'm only going to touch on that briefly, but I am going to show you new and unpublished or very recently published data looking at light applications in real-world interventions. So it, of course, has application to architecture. These are real lighting interventions. Of course, I must start with my conflict of interest disclosure. So these are any past and current commercial relationships in the past 5 years. So I'll just let you have a little look at those. But if I talk about anything related to any of these, I'll include it on the slide. So very briefly, and I'm sure many of you know this work already, we, in collaboration with Bud, we looked at long duration light exposure and its impact on melatonin suppression and circadian phase shifting. And so we have, in these studies, a 9-day inpatient protocol where they have 3 baseline days, a constant routine, sleep, a light exposure during the biological night, because we're trying to induce a delay phase shift in these experiments, then a recovery sleep, a second constant routine, and then sleep before leaving. So these studies initially were, first of all, to see if we gave the same photon density of either a 460 or a 555 nanometer light, what did we get in terms of suppression, shown here, or phase shifting, shown here. And this was a long duration exposure, 6.5-hour exposure, and really to look at the longer effect. And what this work started to show really for the first time is that we have a change in the time course of the response. So you can see here from the raw data in the blue light, you can see suppression pretty much for the whole time except one individual. But then in the 555 nanometer light, trying to promote or at least to stimulate photopic system, there's initial suppression and then it falls off over time. And so we wanted to look at this time course, and we talked about this time course back then. And we talked back in 2003 and then in 2006 about the idea of having this multi-photoreceptor input to the system that had different time constants. And so we have both the photopic and the melanopic inputs to the various brain areas, including the clock and other centers around alerting, that both contribute to these responses, but have a different, potentially irradiance sensitivity and time course. And so the unpublished data to start with, I'm going to show today, was an extension of that initial work. We published the 460 and the 555 nanometer, or most of those data, with Josh Gooley in 2010. But these are now those data plus new data that we've gathered at 420, 480, 507, and a few time points at 620 nanometers, and some dark controls shown here. So this is work, these are data that Josh Gooley collected with others, work that Maria Amundadottir with Marilyn Anderson and I worked on for a thesis, and now Melissa Saint Hilaire is extending that analysis, and these are those data today. So we've looked at the dose response function, or the irradiance response function at these different wavelengths, calculated the ED50, the 50%, or the number of photons we need to get 50% of the response. And then from this, we can create an analytical action spectrum. We, in our analyses, have not assumed univariance. And so, as you'll be aware, the first action spectra from the Brainard and Skeen labs assumed univariance. We have not done that, so the slope can vary in these fits, but we do have a fixed upper and lower asymptote. But the sensitivity, the ED50 slope can change. So first of all, if we just fit an action spectrum to the 6.5 hour exposure overall with that non-univariant function, we get a lambda max, a peak at around 482 nanometers, a little longer than both the Brainard and the Tapan data, but consistent with a role of melanopsin in the overall response for 6.5 hours of melatonin suppression. But that doesn't really tell us the story, of course. We know there's a relationship with time and an interaction. So I'll be splitting those down a little later. Knowing that this is not a univariant response, that there are multiple photoreceptors contributing, we've also modeled the contribution of different photoreceptors. And so we've modeled the melanopsin function. We've modeled contribution of the short wavelength cone and the short wavelength cone and L&M cone combined, again, modeled on the work that Maria Amundadottir did in her thesis. And so if we take the 6.5 hour melatonin suppression response, if we add in the S cone, you can see that there isn't really a great change in the lambda max. We see the same response, a small contribution of S cones overall. And again, if we add in all three channels here, again, this is dominated by melanopsin, not really much contribution from the other systems. But that's taking the 6.5 hours of the light exposure as a single block. And of course, that doesn't tell us anything about the time course. And so, as we did in the Gooley paper, and now extended here, we've broken down the data into the quartiles of light exposure. So this is the first quarter of the 6.5 hours, the second, third, and fourth. Each of these is 97.5 minutes, so just over an hour and a half. And you can see the change in time in terms of the shape of the curve. Again, we're using a free fit in terms of the slope. You can see the change in the slope and in the sensitivity, which is this ED50 value here. So you can see for the 420 nanometers, you need more and more photons to get 50% of the response in this model. Similarly here at 460. And so now we can create action spectra for each quarter of the light exposure and see how they change over time. And so first of all, with the one channel model, really nothing changes. We've already shown that the overall 6.5 hour fit is dominated by melanopsin, and therefore the quarters are. you can see that the goodness of fit of the model does change slightly. At the start, melanopsin doesn't fit quite as well, but then stays pretty much the same for the second, third, and fourth quarters, and that might hint a little at what is to come with the various channels. So now when we put in either the 2-channel or the 3-channel fits, you can see a slightly different picture. First of all, if we look at the top row and show just the melanopsin and S-cone, you can see at the start of the light exposure, the S-cone is contributing about 20% of the overall fit, and then that reduces over time. By the end of the fourth quarter, there's really no S-cone contribution. It's entirely dominated by the melanopsin. If we then look at the 3-channel fits, you can see that at the start, now the S-cone and the LNM cone account for more than 50% of the response. And our lambda max here is 441 nanometers, much shorter than the 480 nanometers or so we've seen overall or in this 2-channel fit. But again, as we go through time, the relative contribution of the cone input dies off, and melanopsin increases. So we go from 47 to 54 to 79 to 92 for the melanopsin. And as the relative contributions of the various channels change, so does the lambda max. By the second half of the light exposure, you can see that the peak is around 480 nanometers, consistent with dominated by melanopsin. So if we look at the first quarter of the light exposure, the first 97 minutes or so, we have this very mixed response, which is dominated by the S-cone, and then over time that quickly reduces. And so this extends the work that Guli and our group showed, where we showed the change just between the 555 and the 460 nanometer data, and showed a dying off of the photopic response, the cone response. Now we've been adding in these 3 channels because we have more data. We can see maybe a more sophisticated change where the cones are contributing at the start and then die off, but in a slightly different manner than we proposed before. Now, when we come to look at circadian phase resetting, of course, we only have a single time point. We measure the clock before the light, give the light pulse, measure the clock after. So we can't look at phase shifting every quarter. There is only one time point that we can look at that. But we've done the same analyses for the phase shifting response, for the fluence response curves, for the shifting, again, without an assumption of univariance. And when we do that, we see a very similar overall action spectrum to that we find for the overall melatonin suppression response. And so a peak of around 480 nanometers, consistent with melanopsin. And that's if we fit just the single model. But if we fit the 2 and the 3 channel models, again, we start to see something different. If we fit just the melanopsin, we get a peak of 484. If we fit the melanopsin and S-cone, we get a slightly shorter peak and a big contribution overall of the S-cone, 69%. And then if we fit all 3 channels, we again get a big contribution of the cone system, dominated by the S-cone, with only about 30% of the melatonin suppression. So now that starts to seemingly, at first glance, create a problem for us, because we have talked about melanopsin being the dominant photoreceptor, being the photoreceptor mediating circadian phase shifting and melatonin suppression. But now here we're saying, well, maybe it's not that at all. It's the S-cone that's mediating phase shifting with contributions for the LNM as well, and melanopsin is only a minor contributing factor. But the reason we don't think this is an inconsistent argument is now we have to start thinking about the impact of light duration and light pattern on phase shifting responses. And we've published over the past 10 years or so a range of different studies where we've looked at the effects of different durations of light exposure. This is white light, 4,000 Kelvin fluorescent. And Amory Chang published in 2012 a dose response going from 12 minutes to 6.5 hours for both phase shifting and for melatonin suppression. And then Shadab Rahman published a few years ago a 15-second and a 2-minute pulse of 10,000 lux light and showed the phase shifting response to those two. And here Shadab has combined the 2-second all the way up to the 4-hour data set to show this dose response in terms of light duration. Now, other work, which I haven't got time to go into today, has also looked at different intermittent exposures. And so Shadab in 2018 and 2019 published papers with different types of intermittent patterns of light exposure. All of which go to show us that there is this nonlinear relationship between light duration and phase setting response that importantly shows that the start of the light exposure is the most important. And so you get the biggest bang for your buck, the biggest impact per minute of exposure with a short duration compared to a longer duration exposure, meaning that the light at the start of the exposure has a disproportionately important effect on the ultimate phase shift and response. And so in the past, where people have sort of thought about the midpoint of light exposure being important, it's the start of the light that is, of course, likely driving most of the effect. So how does that now make sense with our wavelength work? Well, Dick Cronauer, Melissa St. Hilaire and colleagues published a paper where they proposed a dual function pattern, or two functions which explain this duration response to white light, where you have a fast response over the range of minutes, and then from around 12 minutes or longer in terms of hours, you get this change in the function. And this is based on both human and animal data, so I encourage you to go and read the paper published in Journal of Biological Rhythms. But again, this goes to support the idea that the start of the light exposure has the biggest effect. So if the start of the light exposure has the biggest effect and the S-cones dominate the start of the light exposure, then it would look like the S-cones dominate the overall phase shifting response. And so this is not inconsistent necessarily with melanopsin having long duration impact, but we need to start looking at phase shifting responses in response to intermittent exposures of different durations to work out that time course of photoreceptor contribution for different durations of light, which of course we've only done here for 6.5 hours, but we need to redo all this work again for another 20 years by repeating everything for different durations. And I think we're going to find that the S-cones contribute in the early part of the light in a phase shifting response, and then melanopsin dominates for the rest, just like we see for melatonin suppression. But you can't pull that apart in a single phase resetting response. We'd have to do multiple experiments to pull that apart. So we think, have a consistent argument, but it shows that just taking an action spectrum from the overall long duration exposure doesn't really tell you the whole story. So they're the unpublished laboratory data. Now I'm going to move on to our field and applied data using some of these principles. And so, of course, as you all know, light has circadian impact, resetting the circadian clock and ensuring entrainment each and every day. And of course, if we don't get that entrainment right, many things start to go wrong. But in most applications, we're really going to be using the alerting effects of light. Most applications are not dealing with correcting a circadian misalignment. Very few environments cause circadian misalignment, at least in a serious way. So light applications are really to help you maintain alertness when you need to be awake, at work, during the day, or at night at work, and then helping to avoid those alerting effects of light in the hours before sleep to help you fall asleep quicker, have better quality sleep. So light as a non-pharmacological sleepiness countermeasure is really how most people will be applying light, and really I think how we should be talking about light for applied reasons. I think we confuse people by talking about circadian lighting. So I'm going to show you some examples here of many that we're conducting over the past few years. And so I'm going to show the ones in blue here. But as John mentioned, and I'll show hopefully a video later, we are working with the light on the International Space Station. Shadab is working on studies of care home residents and looking at dynamic lighting for care homes. We've just published a paper looking at light information control using intermittent light and exercise during break rooms. And Tracy Sletten and colleagues at Monash University have several papers of simulated and real world night shift applications. So I'm not going to cover those today, but I'm going to show you some detail of our three ongoing and recently completed studies. And so what I've tried to do over the past few years is really change how I talk about lighting for application. When talking to industry, when talking to consumers, circadian shifting is too complicated. We don't need it. Very rarely are you resetting the clock. You might be maintaining entrainment, but often people are already entrained and you're just keeping them on that 24-hour day. And so most places, I think, can be split into these two areas. Environments where people don't sleep. And if you're not sleeping, you need to be alert. And that means high melanopic, high intensity light all the time. No ramping down, no change in the wavelength, not making people sleepy at work. It's all about alertness all the time. And so then we use light as a safe stimulant to improve alertness for the entire shift, for the entire day. We don't need to tune it for the circadian or the non-visual system. It doesn't need to change. You wouldn't want to make people sleepy at work. So why would you, change the spectrum and reduce the melanopic content? But in a place where you do sleep, you do need to change the lighting. In the daytime, in the wake episode, you need to do the same thing as we do where people don't sleep, high melanopic, continuously all the time. But in the hours before sleep, maybe as long as 3, 4, or 5 hours before sleep, we need to deplete that melanopic content and dim the intensity so we can have that light which is not stimulating, which is not as alerting. And that can be a matter of just changing the light bulb, as I'm going to show you in a second. But we don't really need to get into light patterns for different groups, for different disorders. Most people, it's as simple as, if you're not sleeping, be alert, use blue enriched melanopic light. If you are going to sleep soon, dim that down. This is simple to explain, simple for the companies to communicate, simple for the people who need the light to understand. We don't need to complement or to oversell or make claims around circadian that really aren't of use in nearly every scenario. Of course, I have to mention the CIE and the new international units for quantifying light for non-visual purposes, which I know this group knows very well. But I'm going to be reporting the EDI values in the studies we've done. But for those who don't know, this is something you should be using when reporting light for non-visual applications. And it essentially describes the light in terms of its ability to hit the 5 different photoreceptors and provides photopic lux as well. And so it's an easy to use toolbox that will allow you to put in spectral data and get out of it values of EDI, of the equivalent daylight illuminance, which allows us to talk about light now in terms of lux, which people understand, and allow a direct comparison of that illuminance between these different systems. And so this, I think, is a really useful system now to help bring people along into thinking about how to talk about light for this system, because photopic lux is not sufficient, but we can now talk about melanopic or esconopic or other lux values and really help people understand the differences between different sources. And the other very useful thing we can have is the daylight efficacy ratio, which is a unitless ratio, essentially saying what's a relative spectra of the melanopic and photopic contributions. So this is the equivalent of what the M/P ratio used to be in the Lucas toolbox, but now is put into the units that the CIE have developed. And so now instead of M/P, we should be talking about DER. And these are nominal, just my starting points for terms of what would be stimulating or sleep promoting. But you can see here a blue enriched source with a lot of 480 has a high DER, would be alerting. Standard 4000 fluorescence, neither here nor there. Whereas a commercial sleep promoting blue depleted LED that's cut out a lot of the 480 would have a low DER and would be expected to help promote sleep. And so we should be using the DER as well as the EDI value to talk about light. So starting with one of our NASA experiments, this is the human experimental research analog that Shadab Rahman has been leading from our group. And NASA are interested, of course, in light for space travel, because we have to synchronize not only to the Earth day, but maybe to Mars days, maybe to unusual moon days. And so when we travel off the planet, there's often different challenges for us to deal with. In terms of circadian misalignment, Erin Flynn Evans, using data from the International Space Station, shows that about 20% of nights are spent at the wrong circadian phase in terms of sleep. And so here she used a model to predict the temperature minimum each day and overlaid that with their actual sleep patterns from astronauts studied on ISS, and estimated that when they sleep in phase, they sleep about 6.5 hours a night at a good circadian phase, but they lose about an hour per night when they sleep out of phase, which was about 20% of nights during real missions. 6.5 hours is already not enough. Take an hour off that, and now we're starting to get into levels where we're concerned about safety. And of course, this is where NASA wants to do this work. 5.5 hours a night of sleep for potentially months or years on average in this very safety sensitive but dangerous environment is a problem. And so knowing that people are at the wrong circadian time helps us then correct that, and having lighting regimes which will ensure proper circadian alignment is key. We can't be having astronauts flying with only 5.5 hours of sleep. So here is an analog environment at Johnson Space Center. It's a 2-story building in a big hangar where they've created essentially a space station, a space habitat that people live in some of the missions now for up to 45 days, crews of 4. And so they live for a couple of months and then simulate real missions. They have real communication delays, they have emergencies to deal with, they have experiments to do, they have to keep a proper work schedule. This is real isolation. They can't communicate with the outside world other than through NASA mission control. So this is a proper simulation. And you'll notice here, there is some fancy LED lighting, which I'm going to show in a second, which is part of the LED, similar to the LED lighting that we've been working with this for the space station. And so in the missions that we were involved in working in, they were 45-day missions with a chronic sleep schedule. I'll show you in a second. And we had 5 teams of 4 because one of the missions was cut short because of Hurricane Harvey. And so in 2 of the missions, we gave a standard lighting schedule, which was just what was already in there. And I'm going to show you those data in a second. So we just used whatever lamps they'd already had fitted. And then for the dynamic lighting schedule, we changed that to have blue enriched high melanopic lighting in the daytime and blue depleted lower melanopic light in the evening. Our main aim was to assess circadian phase from urinary 6-sulfathoxymelatonin. We also have sleep and cognition data as well, but I'm just going to focus on the urine data today. And so we hypothesized that deploying the dynamic lighting schedule would improve the rate or the maintenance of circadian adaptation compared to the static lighting schedule they already had installed. And of course, this is linked to and is testing some of the technologies we already now have on the space station. So just to show you the mission and the sleep, this is the 45-day mission here on the y-axis, clock time on the x here. And here you can see the sleep schedule. So they had 3 nights with 8 hours, 5 nights with 5, 2 of 8, 5 of 5, 2 of 8, 5 and 5. So they cycled through this, if you like, weekend. They got 8 hours of sleep for 2 nights, and then weeknights. Then they got 5 hours a night over the Monday to Friday. We measured the urine every week, and these are this is the acrophase or peak time of the urinary 6-sulfathoxymelatonin for one person. These are the performance test times. You don't have to worry about those today. But you can see that the light didn't change through the wake episodes. The lights were just on all the time while they were awake and then turned off prior to sleep. So there was no change in their lighting schedule. In the dynamic lighting, we did change some things. So we went in and changed all the lights in the unit, and in the paper when we publish this, we'll have the table of what the old lights and what the new lights were. And we fitted a mixture of both static and tunable lighting to be able to alter the spectrum and intensity. And so here we have, again, the same schedule, but during the wake episodes, they're exposed to a blue-enriched high melanopic light of around 6,000 Kelvin. I'll show you the real data in a second. But then for 3 hours before sleep, we started them on a lower intensity and lower blue light for 2 hours. And then for the 1 hour before sleep, they had an even lower melanopic and lower intensity light in the hour before sleep, whether that was before an 8 hour sleep or before a 5 hour sleep. And again, we measured the urinary 6-sulfatoxy melatonin once a week in all of these participants. So for this group, of course, it's important that we go into the detail of the lighting, and these are the data. Of course, we have many more, we'll publish many more, but these are the data to show that our intervention worked. So these are data measured at 72 inches, so 6 feet, 1.8 meters in the horizontal plane, looking up, essentially. So this is the idea being that this is the maximum light you could get. We also have some vertical plane measures, again, which we'll publish. And we have the SLS and the DLS, the static lighting and the dynamic lighting, and then we have the different levels. So this is level 1, and we measured light in 6 locations, and then averaged the measures at 72 inch up during the day, in this case, and then evening here. So let's just look at the first row for daytime. First of all, you can see that just if we use color temperature, which obviously isn't a good enough marker, but just as a guide, during the intervention, we did increase the color temperature of their light exposure. So it's gone from 42 to 6,300, 37 to 54. The intensity of the light has increased in some places. So in level 1, we about tripled the photopic lux, but on level 2, we didn't really change the photopic lux. If now we look at the melanopic EDI, we sort of quadrupled, maybe even a little bit more, the melanopic EDI, because we've got a higher intensity light and a blue enriched source. So we have a much higher melanopic EDI and a small increase in melanopic EDI in level 2. And then if we look at the DER, so higher values telling us it's a more blue enriched source, then you can see we increased the DER in both level 1 and level 2. So in the daytime, we had people exposed to more melanopic light. Now, if we go to the evening, where of course we're trying to reduce the melanopic content, we were able to show that we could do that too. So now we've dropped the color temperature between level 1 and level 2, and then the DLS versus SLS. We've reduced the intensity in terms of photopic lux, so the DLS just under half in terms of intensity, a big reduction in level 2. If we look at the melanopic lux, we've cut the melanopic lux by 2/3 on level 1, but by much more than that on level 2. And again, you can see the change or similarity here, but the change at least in level 1 in the DER. And then when we look at the bunks were quite brightly lit, and even with our intervention, we're still quite brightly lit. But again, we reduced the color temperature, reduced the intensity, reduced the melanopic lux, reduced the DER. So we were able to do this in a big facility just by changing the light bulbs from what they already had. And it was a mixed light bulbs. It wasn't just the one we've used on space station. There's all sorts of different lamps included here, but we chose ones that had higher melanopic or lower melanopic content for use at the right time of day. So what did that do to their rhythms? So here are examples of urinary 6-sulfatoxy melatonin rhythms just from one of the individuals. The raw data are shown in the black circles, and the fitted cosine function is seen there, with the peak time shown here on the left or right. So this individual, before the mission, 10 days before the mission, had a sulfate peak at about 4 a.m., exactly where it should be. The normal peak time should be at about 4 o'clock in the morning. On the 5th day of the mission, they drifted a little bit to 6 a.m. By day 12, just after 7. By day 26, even a little later, a bit close to 7:30. So we had 2,231 urine samples, about 146 phase assessments, and everything was significant when we fit it with the co-samples, except one, which I'm accepting at 0.06 for 1 out of 146. So now, what was the pattern of the change in the groups? So if we look at mission 1 and mission 2, which were the control lighting, the SLS lighting, you can see that we saw a drift in circadian phase. These are all the individual data, the 4 people in each mission. The gray shows the range of normal phases, which is quite narrow. And this is based on half a standard deviation, plus or minus half a standard deviation of the average. But the reason it's so tight in this particular analysis is because their scheduled sleep meant that they didn't have the freedom to expand their phase because they were made to go to bed for 5 hours a night in the week and had to get up at 7 o'clock. So it would be silly to say, well, the normal range should be from 1 to 7, because then it would always be normal, and it's clearly not the case. And so we had this tight range of what we considered normal for this study. And then wake time is here in the blue line, which is 7 a.m. They had to wake up at 7. So if you look at the timing of the sulfate acrophase, many of, as we went through the mission, they were waking shortly after or even before their sulfate acrophase, which would be the equivalent of waking shortly after 4 a.m. or even before 4 a.m. in biological time. So this is bad. People are waking up in the middle of their biological night and are going to feel bad when they wake up and not perform well. Now, if we look at the missions 4 and 5, we see a different picture. We see that they maintain a better alignment with the normal phase range and with the wake time. None of the people in the control in the DLS missions wake up before their peak in 6-sulfatoxy, and this phase angle, the gap between sleep offset and sulfate, is much better. It's much wider. And again, you can see here in mission 5, very nice maintenance of entrainment of circadian rhythms during the condition. We've excluded mission 3 from the grouped analysis because they didn't do the light exposure properly until day 11. But after day 11, they did maintain a pretty good light intervention, and you can see that they maintained a pretty good entrainment as well. But we've excluded it from the group analysis because we're not sure to what extent they did it properly for the first 11 days. But if you look at the group data for the 1 and 2 versus 4 and 5 missions, you can see on average, the sulfate peak stays in the normal range for the DLS mission, the dynamic lighting, whereas in the control group using their standard lighting, much bigger drift and much more sleep at the wrong phase. It was statistically significant at day 19 if we just look at the comparison between the 2 groups. But you can see overall we've got a much better profile with the dynamic lighting. If we look at the percentage of time that mission days were spent misaligned or not misaligned, in the SLS, in the static lighting, they spent 89% of mission days sleeping at a phase where the sulfate was after 5 a.m., so the wrong circadian phase in our definition. It was only 36% in the experimental condition. If we look at sleeping, waking at the completely wrong circadian phase, so in fact waking before your sulfate peak, it happened in 16% of the days under the static mission. It never happened under the dynamic lighting. So even if we look at the average acrophase, or we look at the phase relationship between the average acrophase and sleep, by these definitions, there's much better circadian alignment under the dynamic lighting. Now, these are the lighting systems that have gone to the space station that Bud Brainard's lab with John and myself and Shadab, Melissa and so on are looking at. So they're being fitted now, they're nearly all in. And we're looking at the same type of idea where we have high blue, high melanopic lighting in the daytime or work episodes, and then blue depleted, low melanopic for as long as possible before sleep.
It can be a little noisy, but it's very quiet in here. And we can control light with a light switch. If we are just middle of the day, we have a light like you're seeing right now, which is just this kind of standard lighting. It's getting close to the end of the evening. You want to dim the light a little bit, kind of for the end of the evening. Or if you're going to be up late and you need to keep awake, we have a really bright light setting. The other thing we have is off.
So that shows you the real lighting on the real space station, and the changes that they can make. Of course, they could have very many more settings than that, but those are the 3 settings that we've put up there and are testing at the moment. And so we now have all the data back to look at circadian entrainment. We collected urine samples on the space station. We have sleep, we have performance. And so we're going to be repeating that type of analysis you saw for the HERA mission with our ISS data. So just in the last 10 minutes or so, I just want to show 2 other examples that we've been doing, which I think are of interest in terms of their approach. So first of all, working with Laura Connolly, who's a PhD student at Monash University, and Professor Jenny Ponsford, who leads the traumatic brain injury work there. We've been looking at using light in patients' homes to help with fatigue and sleep problems associated with traumatic brain injury. And so a few years ago now, we did a light box study where we could show that being exposed to blue light in the morning as opposed to yellow or control, no treatment, was able to improve fatigue in patients with traumatic brain injury. And since then, there have been a number of studies following up on this to show that we can use this light box type therapy for helping with some of the symptoms of brain injury, which include fatigue, sleepiness, sleep disorders, and so on. But rather than sit in front of a light box, what we wanted to do with Laura is to see, can we take the treatment into patients' homes? And of course, this would apply not just to brain injury, but to seasonal affective disorder. It could apply to dementia. It could apply to geriatric populations. How do we make the light, how do we make the home the light box, essentially? And so these are unpublished data. Laura has these submitted. But just to show you briefly what we did, we went into people's homes, we assessed their current lighting, and then we changed it. We either changed it to make it look like it already did, which is the sham control. We essentially put back in the same lights. Or we fitted, just like for HERA, better lighting for daytime and nighttime and told people how to use the lights in the day and the evening. And so we had 24 patients in a 16-week intervention where we crossed over 8 weeks of the treatment or dynamic light, 8 weeks of control, with half of the groups getting it in separate orders. And again, this work is under review and in Laura's thesis, but you can see what we've been able to do in terms of the lighting conditions. So in the daytime, we want higher melanopic lux, and we achieve that. We have higher photopic, higher color temperature, higher melanopic lux, higher DER, just like you saw for HERA. But then in the evening, we want lower melanopic lux. So we've got lower overall photopic lux, lower color temperature, lower melanopic lux, lower DER. So, and these are again 72-inch measures in the horizontal plane, although we have many others. So this is a real environment. People have still got access to daylight. They're living their normal lives, but now we've made the home the therapy. And we didn't see changes in fatigue, but we did see a significant difference in sleep based on the Pittsburgh Sleep Quality Index and sleep based on the Insomnia Severity Index. And so we were able to show in this really small pilot study to start with that home-based therapy is able to treat some of the symptoms of brain injury. And so we're going to continue this work to increase the power, but you know, this could be expanded to many other groups to really make light therapy much more accessible and really become part of your ambient environment. The home ideally does it for you. Now, finally, a new paper that's just been published that I think extends what we're doing in lighting to a new level is a piece of work where we've looked at the impact of lighting on medical error rates. And so this was a study done with Judy Chen and colleagues at the University of Wisconsin, where we changed the lighting in the nursing units and break rooms of a university hospital ICU. And this has just been published. And we used a blue enriched LED light source fitted into the nurses' workstations, corridors, and break room. Here you can see the SPD for the original lights, which were just standard fluorescent lighting, as you can see, and our blue enriched white LED in the various places. Here you can see again the data, and so if we compare pre and post, there's a before after study. You can see that we increased generally the overall photopic lux, we increased the overall melanopic lux, and you can see we had a much higher DER light source, a much more blue enriched light source, which you can see here. We did a before after design, but we controlled for seasons. So the study was January to May across 2 years, and so we took at any seasonal differences, and we used a very objective assessment here. And this is the sort of approach I think we should be using now to get away a little bit from subjective or psychomotor performance tools, which we all believe as scientists, but it's hard to convince businesses to change based on that. But here we looked at medical error rates, and so we had trained nurse reviewers look at medical charts retrospectively using a trigger tool where they look for words and phrases that tell us something about medical errors. And then those events were classified, or incidents were classified by 2 physicians who were blinded to the condition to determine if it was an error at all, whether it was harmful or non-harmful, what the harm level was or the severity was, whether it's preventable or non-preventable. And so the nurses reviewed just over 1,000 charts, identified 300 incidents, and then the reviewers rated them into these categories. And I'll show you those data now. And so first of all, and if you read the abstract for the paper, it says there was no difference between the lighting conditions in the rate of incidence. And that was true if you looked at the overall rate. And so these data here show there's really no difference if you just look at the harmful versus non-harmful errors. There was no difference between the 2 conditions in the pre versus post intervention. And looking at the incident, whether you classified or include things that even weren't harmful, there was no difference. And that was what our primary aim was. And so in the paper, that's what's in the abstract. But we did do an exploratory analysis where we looked at the difference based on severity of the medical error. And this was based on work that our colleague Chris Landrigan, who's a co-author of this work, who's an errors expert. Often you would just look at the serious errors rather than all errors. But we didn't propose that as an a priori analysis. And so this is exploratory. It's in the paper, but the journal wouldn't let us put it in the abstract. But if you dig down a little bit, you find that if you look at the high severity harmful errors, the serious medical errors, we do see a significant reduction in the rate of those, about a 33% fall. And so we think this is good evidence of having a real impact on nursing performance, which in turn affects patient safety with a hard outcome, medical errors using anonymized chart review. This, you can't really argue with that as an outcome. And we can see this impact of lighting, even though we didn't power the study for this when we have to consider it exploratory. But very encouraging. And even if you look at some of the other outcomes, they did reduce, they just weren't significant. So you can see there was a reduction if you take all errors, about an 18 or a 13% reduction, depending on which method you use. And these measures also reduced. They just weren't statistically significant. But we think this is very encouraging. But we should be using these, if you like, harder outcomes that people already used in other fields and respect and know mean something if we want to really show that light is having an impact on safety, productivity, performance, and so on. So I'm going to really stop there in a couple of seconds. So we have done work on architectural design, mainly in collaboration with Marilyn Anderson and colleagues, and we've published a series of papers and proceedings where we've looked at, do different environments reach a certain threshold of light in terms of thinking about circadian thresholds. You'll all be aware, I'm sure, but just to reiterate, the Manchester group that created the Lucas toolbox has now met again and has a report under review where we're recommending levels of light in terms of melanopic EDI for daytime, evening, and sleep. And so in terms of architectural design, if we're going to use a threshold to say if a place meets its threshold, these are now some new recommendations from this expert group, which you can now start to look at, and we can start to debate whether these are the right levels based on different environments. And of course, as I presented last time at SLTBR, we have software now where we can model circadian light, looking at the melanopsin contribution to a space. And if you haven't seen this, I would encourage you to go and look at the tutorial for this software. Look for Solema, Alpha, and Vimeo, and you'll find it, where we're able to now put every aspect of a design, the light source, the glazing, the furniture, the carpets, the wall paint, and give it a circadian value to make sure that your environments are consistent. We don't want nice blue and rich lighting in the ceiling, but orange walls. That's not going to help the people sitting in the space. So I'll finish by thanking, first of all, my colleagues at the Brigham Women's who've really led a lot of the work I told you, Shadab Rahman, Melissa Saint-Hilaire, Brianne Kent, and Josh Gooley, who did those original wavelength studies. Maria Mundadottir with Marilyn Anderson, who did the analysis of the time course, which Melissa is now continuing. Laura Connolly, the PhD student doing the work at Monash University, and Judy Chen, who is the lead of the University of Wisconsin study with medical errors. And of course, my introducer, John, and Bud Brainard, without which really none of this work would have been inspired. Thank you very much.
Thank you, Steve. So we have a number of questions, if you have time.
Of course.
All right, excellent. I'd like to correct a mistake that I had in the introduction. The virtual meeting dates are in May 19th to the 21st. So do check out our website. The program will be posted. The dates will be confirmed. You'll get a sense of what the program will be by looking at last year's proposed program for a meeting that we couldn't hold. So the first question we have here, Steve, is does the contribution from the different opsin systems vary with circadian time?
It's a great question. We haven't looked at that. Our light exposures are timed to be at about the same circadian time because we want them to be light exposure which cause a delay. And so there's about a 3-hour range of circadian phases that we permit in the study. We had, I think, one individual in all of our studies where we gave the light at the wrong time because they had an unusual phase angle and they were removed. So we haven't actually gone within the 3 hours to see if it varies even more, but we would only have a fairly narrow bin of time to look at that. My personal opinion in terms of the alerting effects of light, I don't think there is a circadian input to that. I think it's pretty much an on or off response for many of these effects, even for something like melatonin suppression. We don't see a change over the night in melatonin suppression. It seems to be a fairly consistent, relatively on or off response. So I don't think there's a big contribution of circadian time to these, but we don't have a wide enough range to look at that for the shifting, I'm afraid. But it's a great question.
Moving on, virtually all prescription glasses include blue light filters. Is this a concern?
Well, it depends what we mean by blue. And so if they're a blue light filter, to think about light safety, they're blocking primarily the 450 nanometer region of the spectrum. That may not be impacting the 480 nanometer for the non-visual. And so I think we have to start talking about blue in slightly different ways to differentiate the different wavelengths within what we call blue. So what blue is being filtered? And then it really depends on intensity after that. If there's enough light in the environment, if you're in daylight, then filters probably don't matter because there's still going to be enough light getting through at that wavelength to have the impact. But if we start to get into dim light environments, internal evening environments, then we're very likely to have an impact there. And so knowing the spectrum, the transmission spectrum of any lens, I think is important if you want to try and work out if it's going to affect the visual system or the non-visual system or both. And the bigger concern is when you're in dimmer indoor light, I think, for that.
Excellent. So the CIE toolbox metrics, do they consider duration and time-dependent effects?
No, and I think that was intentional. I wasn't involved in creating the toolbox itself, but I think that's intentional because this is really about quantifying light. It's not yet talking about how to interpret the quantity of light. So the point of the Lucas toolbox and now the CIE is to have us all using the same units to describe the light exposures we give, so we can start comparing and contrasting. But it doesn't say anything about the biological impact of that light on suppression or phase shifting or alertness, and it doesn't intend to. And the sort of work I showed you where we measure it in a fixed way using the CIE tool, and then we look at the data and how it changes over time, that's for the researchers to do. The CIE is just really telling us how to measure the light. But as we all use it more, I think we're going to find more and more interesting effects due to duration, due to intensity, due to pattern, and we'll be more easily able to compare people's experiments by using the same units.
Indeed, work to be done. Moving to your HERA studies, do you have any data on the quality of sleep during any of the missions, or specifically mission 1, this person's asking?
Yeah, so thank you, Janice. We have a sleep quality, we have a sleep questionnaire. So there is a post-sleep questionnaire. So we do have a measure of subjective sleep quality. That we don't have polysomnography in these data, so we can't speak to the quality from that point of view. The problem with looking at things like the sleep and even the performance in those data, the sleep episode is restricted. And so if you've only got 5 hours to sleep and you're very tired, you're just going to sleep the whole time, most likely. And so subjectively, you might not really be able to tell that. And the performance testing is done relatively infrequently, and also sometimes during the wake maintenance zone. And I didn't get into that, but because the performance testing is usually in the evening, some of those tests are in the wake maintenance zone, and so are not really able to tell you anything about sort of ongoing baseline performance. So we do have some of that, but I'm not anticipating the sleep and performance data to show as much. They've not really been collected in the way that would allow us to best able to answer changes in those.
And did we look at visual aspects such as the Farnsworth-Munsell?
Well, Dr. Hanifin, I'm going to let you answer that question for ISS.
Well, for ISS we are, yes, but
yeah.
I think for the HERA study we did not.
No, we didn't. So, but it's obviously a concern. So in the ISS mission, John and Bud Brainard and others, in fact, created new tools for the first time to measure visual function on the space station, and so we do have data to look at that in the space station. We have a light questionnaire in the HERA mission. We did ask people about safety and side effects. So we do have a little bit of information about visual function, but we didn't, specifically measure those things during the mission. But it's something we're always thinking about in terms of making sure we can maintain good visual function as well as non-visual.
Moving on. So circadian shifting feature of dynamic lighting, would it work with just keeping the color temperature the same and increasing intensities?
At a certain point, yes. Now, I used the CCT values again, just so people could latch onto that. But remember, CCT is the wrong unit. We shouldn't be using CCT. As we continue to use the CIE tool more and more, we will be stopping using CCT as a way to describe the light. But as we're in that transition, I included it. So yes, you could do that, but then there are interactions with intensity. So yes, you could probably get the right amount of melanopic EDI with a very bright 3000 Kelvin light, but then you'd have to use much more of the light to get the effect. So why would you do that? Why would you use a light where you have to use more energy to get the threshold that you want to achieve? We need to save energy. And so why wouldn't you use a light source which is much more efficient in obtaining the spectrum that you need? And so, yes, there is an interaction, of course, between spectrum and intensity. They are changing together. At a high enough intensity, if you're in sunlight, it doesn't matter. You've got so much of all wavelengths, it's not going to make a difference. But when we get into our indoor environments, then we should think about that. And rather than just ramp it up and waste energy, let's just use the right light at the right time. It's not difficult, as I showed you for our home-based studies.
Thank you. Continuing on, dynamic lighting, excuse me, home-based therapy lighting, home-based lighting therapy, and insomnia.
So I think it depends what. Sorry, John.
Go ahead.
No, so it depends, I think, what type of insomnia people have, and so we published a few years ago now a study where we measured circadian phase in patients with primary insomnia, and between 10 and 20% of those patients, in fact, had a circadian disorder. They didn't have insomnia, and so in patients who have symptoms of insomnia because of sleeping at the wrong circadian phase, then I do think a home-based therapy like this with brighter morning light, brighter blue-rich morning light, better evening light, dragging people's circadian rhythms back to a better phase angle would help. But if you've got insomnia due to another reason, then it may not. And sleep maintenance insomnia probably, if you're already sleeping in the dark, then maybe that wouldn't be as useful. But I do think thinking of how this home-based therapy can be used in many different groups, first of all, to provide stability to your day-night cycle, which will help the circadian rhythms of all of us. So helping to maintain that good phase angle of entrainment. And then where people need a bit more help in doing that, it just makes it easy for them to do, hopefully, as we did with the brain injury and treating some of the symptoms of depression and seasonal affective disorder and so on. There are other benefits of light beyond just the circadian. So I think we should look at this for many different aspects, but it might be better or worse depending on why people have those problems.
The next question has to do with the dynamic lighting system. I'm guessing in the HERA study, it seems to be lower than what Bud has talked about on ISS.
Okay, thanks, Michael.
So do you want to comment on that, Steve? I'm not entirely.
Yeah, I wouldn't know. I don't know what levels you're referring to when Bud has mentioned that, but we will do that comparison, of course. So what we do have in both environments are light meter data. And so Bud, John, Tony Clark and colleagues in our ISS mission got a spectrophotometer into space. And so we have spectrophotometer readings on the space station and also in the HERA mission, so we can make those comparisons. So we haven't done that yet. We will do that going forward to compare and contrast the two. So we'll have more information on that in the next few months.
Two questions to wrap up. Where is the light measured for CIE toolbox?
Yeah, so you can measure the light anywhere. We tend to try and measure it at the eye in the vertical plane. So, put the light meter in front of the eye, looking straight ahead. I don't like talking about angle of gaze and don't do angle of gaze measures because gaze can change a small bit and light changes completely. It's really about measuring the environment so someone else can repeat that environment in another experiment. So when I say we measure at the eye, it's nothing really to do with the eye. It's at a fixed height in a fixed orientation. So it's either vertical at 0 degrees looking straight ahead, or for the data I showed you today, it's in the horizontal plane at 72 inches looking straight up. The idea that if you stood and looked up, that would be your maximum exposure. It doesn't matter really, I think, where you measure the light, as long as you describe where it is in the space, where it is from the light source. So someone can then go and recreate that light environment in future studies. So don't mistake me, I'm not trying to say always that what people are seeing at the eye. It's in a fixed place in the space, which we've tried to make equivalent to where the eye would be, but I'm not talking about angle of gaze. It's about describing the environment, because we don't know what's hitting the eye, getting into the eye, getting into the retina.
And lastly, too much blue light, is overstimulation an issue?
I personally don't think so. Sunlight has huge amounts of short wavelength light. We wouldn't think that daylight would be overstimulating. We don't worry ourselves about that. Any light level we produce indoors is orders of magnitude below the light level you're exposed to in daylight. So for most environments, I don't think that's a problem. There may be patient groups where we might need to consider that. So one group might be people with bipolar disorder. There's been mention of the risk of overstimulation with light that might increase the risk of a manic episode, but that's not systematically been systematically studied, but is a potential concern clinically. So yes, you need to think who you're doing this with and why and what's it going to do to them. But in general, if we're less than daylight, then we're well within something that we're used to seeing every day, hopefully.
Thank you, Steve. This was an excellent talk. I really appreciate your time, and I know we went a bit over, so thank you.
Sorry, my fault.
No, not at all.
Thank
We
you.
had some good questions. Thank you.
Thank you, everyone.
And let's see.